on day one of this unit, we talked about throwing something up in the air and then having it come back down, and how you used to always just throw it straight up in the air, and that all we would actually be modeling is height versus time, and that the important distinction in this chapter that we could do is not just height, but also the horizontal distance. So actually, as it's traveling up, we can see how far over it's gone as well. So to remind you, the way that we are setting these up is that y is equal to some sort of height, and that x is equal to some sort of distance. And so when we throw something up in the air, it makes this parabola type shape, which we call a projectile. Okay, so we're going to be modeling this projectile motion. And back when it was straight up, which is how you used to do everything, it was always modeled with h of t equals negative 16 t squared plus an initial velocity times t plus an initial height. And what we're going to do is allow us to not just throw it straight up, but throw it at an angle as well. Okay, so at an angle, the y equation only changes slightly. Okay, so it's still negative 16 t squared. It still has initial velocity, but this time, in order to account for the angle, we include a sine theta times t plus an initial velocity. We also have an x equation now, because we're not just going straight up and down and straight back. We're going to actually travel in the horizontal direction. So it's basically this part of the equation. This negative 16 is what makes it go up and come back down in the y, and the x isn't doing that. It's not going out in the x direction and then coming back. So it's just an initial velocity and then cosine theta times t. We got cosine's an x value, sine is a y value, plus some sort of initial x value. And that's basically what we're going to be exploring for the next couple days, is these sets of parametric equations, which model projectile motion. So example 1 is what you're used to, what you did in Algebra 2, and what we did earlier in the year when we were dealing with this type of stuff. We have a projectile motion that's going straight up, so it's a one dimension, which means that we don't have an x and a y, we'll just have like a y and a t. So for this one, we can just have h of t equals negative 16 t squared plus the initial velocity plus the initial height. And we just have a nice table of values that we need to figure out. And it's actually really easy to do this on the calculator. So we could basically just evaluate this when t equals 0, and we'll get 75. Evaluate it when t equals 1, we'll get 135. When t equals 2, we'll get 163. When t equals 3, we get 159. And at 4, it's going to be 123. And at 5, it will be 55. The last one is asking us at what time does this equal 0? So in order to do that one, we have to do the quadratic equation. Okay, so I'm just going to clear some space for myself, and if I set this equal and I need to solve, I'm going to let a equal negative 16, b equal 76, and c equal 75, and I'll just plug this in to the quadratic formula for us. Okay, so I do that, I'm going to get negative 0.83 and then 5.5887. So negative time doesn't exist yet, so I know that it's going to hit the ground at 5.5887. I'm going to go over how to program the calculator to make the quadratic formula for us so that we don't have to spend as much time doing it later. So I'm going to start off by hitting Program and go over to New, and I'm just going to enter a name. So I'm going to call this one Quad Form for Quadratic Formula, if I can find all of the letters. Okay, so there's Quad Form. I'm going to hit Enter. So now I'm in the program. I just like to hit Enter another time just so that the first line is empty. So in case I accidentally go in here, I don't clear things by accident. Once I'm in here, I'm going to re-hit this program button and go over to this input output. And what I want to do is prompt. So what this is going to do is prompt the user, aka you, when you run this program, for things. And what I want to prompt it is the letter A. So I'm going to do alpha A, comma, alpha B, comma, alpha C. So I want it to ask you what A, B, and C are in the quadratic formula or quadratic equation that we're working with. I'm going to hit enter. And now I'm going to write in the quadratic formula. I'm going to add a couple extra parentheses probably, because I'm not sure how fancy this program is going to write when I go to do it, but I'm just entering the quadratic formula. Good, it is writing it in the kind of dumb way. So this will look the same for all of our calculators. But I'm just entering the quadratic formula in there. So we have negative b plus the square root, b squared minus 4ac. I'm going to close the parentheses for the square root. I'm going to close the parentheses one more time, which is going to close the top part. And then I'm going to divide, open a new parentheses, 2a. Close the parenthesis for the bottom and close it once more. And then I'm going to store this as alpha x. Now, it's important, since we're already in parametric mode, that you switch this to x. Don't hit this one yet, because we're going to use that next time. So that's the first one. And now you just repeat this again. And this time you do a minus there, because we have to do the plus or minus part. Whoopsies, hitting the wrong buttons. This is so much fun, isn't it? Aren't you having a blast? Did you like my song? All right, once you get here, we're going to store this one as t, and that's because I know that it just so happens in all of these situations, whenever the negative sign is here, it's going to give us the actual t value that we want, and since we're in parametric mode, we'll be able to hit this button and it will always give us this second answer. Once we have these entered, what we need to do is ask them to display. So I'm going to hit the program button again, go over to this input-output, and ask it to display. Now, I'm a big fan of making them display on two different lines, so I'm going to do display alpha x, hit enter, and then go back into program and go back to display and ask it to display t this time. Now, if everything is working perfectly fine, we can just hit second quit. And let's just test run it by doing the quadratic formula that we just did for the last example. So I'm going to hit program and just hit enter. Hit enter one more time. It asks me what a is. I'm going to do negative 16. It's important to use the negative and not the minus. The b value was 76 and the c value was 75. And here are the two values that we got when we did the quadratic formula before. And it stored t as the positive one, the one that we care about, 5.58. And if we wanted to get the first one, we do know that it is just stored as x. Now, I'll remind you that these x's and t's don't matter once we go up here into the y equals. They are automatically ignored if they are stored elsewhere in the calculated vet. So hopefully you were able to get that up and running by following the directions. Woo! So I know I already went over this at the beginning of the video, but here's where it formally falls in the notes. We have modeling projectiles. Okay, so for the x and y equations here, we have the x value is going to be the initial velocity cosine theta. So that's the velocity just in the x direction. Okay, that's what the cosine theta does. It scales down the velocity. So like if we had a vector, let's say right there, remember that vectors are defined as the magnitude cosine theta, magnitude sine theta. So basically just grabbing the x value of that, and that's the new velocity for me. And I need to multiply that by t. It's really important that the theta is inside of cosine and the t is outside of. And then I just have some initial value. And the y equation is similar to what we used to do with the negative 16t squared plus initial velocity, but this time we will use this new velocity that's just in the y direction. Okay, so it just takes the y component, and again, really important that theta is in the parentheses, but t is not, and then some initial height. So if we were to revisit what we just did with example 1, what we had when it said straight up is that theta actually equals 90 degrees. That's going straight up. So if we plug this in, we would get x equals, and then the initial velocity was 76 cosine 90 times t. Well, cosine of 90 is 0. So 0 times t equals 0. So there was no x value, and that's why in Algebra 2 and what we did earlier in the year, we never bothered to say that there was another direction here because we were always going straight up. And when we look at the y equation, it's negative 16t squared plus 76 sine, not cosine, sine of 90 times t plus the initial height. Well, sine of 90 is equal to 1. So that's just going to become 76t, the equation that we had in the first example. So that's why whenever we did this stuff, it was always straight up, because it basically eliminated the x equation and it made the y equation very easy for us, where we just needed to say what the initial velocity was in the y direction and didn't need to think about anything else. There's one other thing in this section that's important, which is wind. So for us, when we're talking about wind, we mean wind or wind gust, however we word it, depending on the question. We're always talking about an instantaneous wind gust which affects the initial velocity. Okay, so that means it's only affecting the initial velocity of these things. And more importantly for us, we're actually never going to let it affect the y value and only horizontal direction. So when we're doing wind, it's either going to be helping the x value, which means that we would add whatever the wind speed is times t, or it will be hurting, which means that it's going in the face of the x value, which would be a minus the wind times t. And we'll do some examples with this so you see what I'm talking about. But essentially it modifies this part right here. At the end of the x equation, we're going to include the wind by either adding or subtracting it, depending on whether it is moving in the positive or the negative x direction. All right, for example 2, we have Jack Attack at the 15-yard line, and he kicks a football downfield, initial velocity 85 feet per second, angle elevation of 56. There's a wind gust blowing horizontally in Jack's face at 15 feet per second. So the first thing I'm going to do is actually eliminate that 15-yard and make it 45 feet. There's 3 feet per yard, so 15 times 3, 45. So step 1, let's write Jack's equations. So we have the initial velocity 85, cosine of the angle 56, close parentheses, t. We're going to have plus 45. That's, remember, the 15 yards. That's saying that if one end zone of this football field is 0, then he is 45 feet away from that. And then we have this horizontal wind gust blowing in his face, which means it's going to slow down or subtract 15t. So that's the wind speed times t. And for the y equation, we have negative 16 t squared plus 85 sine 56, close parentheses, t. And they didn't tell us if it's above the air at all, so we're just assuming that it's plus 0 over here. And then I have that t has to be greater than or equal to 0. So this is my set of parametric equations for this situation. In order to find the maximum height of this, I just need to focus on the y values, because that's what height is. And I know that it forms a parabola shape, and that the t value of the vertex in this case, okay, because we're defining things in terms of t and y, the t value of the vertex is going to be at negative b over 2a, and if I plug that into y, that will tell me what the y value is. So negative b, that's going to be 85 sine 56, no t included, the b is the number in front of the t, over 2 times negative 16. Now let's type that in the calculator. I get 202. We want to make sure that we store that value. And then I'm just going to plug that directly in to the y equation, and I will get 77.59 feet. So this football is reaching a maximum height at 77 feet, which is 2.2 seconds after Jack Attack kicked it. Next question is, what is the hang time, which is basically how long is it in the air for? So this football is going up in the air and then it hits. So what I want to know is, when does the hit the ground, which is when y equals 0. And in order to do this, we need to just use our quadratic formula. So I'm going to write what a, b, and c are. And then I'm just going to enter them into the program in the calculator. It's important to me that you actually write all of this stuff down as well, just so that you're showing your work, even though the calculator is doing all the heavy lifting for us. Marking down that I store it, but I don't actually need that for this particular part, but that is the answer to this question. It is in the air for 4.404 seconds. That's a lot of fours. Now for how far downfield the football will first hit the ground, I'm just going to take this value that we stored and I'm going to plug it into the x equation. So when I plug it into the x equation, I get 188.27 feet. Now, there's a couple things that I need to do here. First, in football, everything is always in yards, so I'm just going to divide this by 3, which is going to give me 62.75 yards, give or take. And then what I want to do is take into account those 15 yards that we started with, because this x position is from 0. So if 0 is way over on the edge, and we started 15 feet in, and this landed 62 yards in, we just need to subtract that 15 yards, which is where we started. So this will have traveled 47.76 yards. For question 3, got a tennis ball being hit 3 feet above the ground, initial speed of 150 feet per second, that is very powerful, at an angle of 18 degrees with the horizon. So first thing I think we should do is just write our equations. So we'll have x equals 150 cosine 18 times t. Y is going to be negative 16 t squared plus 150 sine 18 times t. And we have plus 3 because we had an initial height. And just in the interest of board space, I'm going to put the t value up there. That's just greater than or equal to 0. So for part A of this, we're being asked, will this clear a wall that is 350 feet away and 20 feet tall? So essentially what this is a collision question. We have another set of equations, x equals 350 with no t, and y equals 20 with no t. And we want to know basically, do we collide? So our first step when we're doing collision ones is always to set x equal to x to find the t value. And once we have that, then we compare the two y values. So that's what process I'm going to follow right now. So the x equation, setting equal, is going to be 350 equals 150 cosine 18 times t. I'm just going to solve that for t by dividing. So I'll get 350 divided by 150 cosine 18. Be real careful how you type that into your calculator. And I will get approximately 2.45 seconds. I'm going to make sure to store that value because that's the time when the x's are equal. So I'm just going to plug in to the y equation. So I'll get y of 2.45 using the exact value. I'm going to get 20.4. Now if I compare that to this static 20 right here, that is greater than it, which means that this is going to clear the wall. Now, if the value we found was less than 20, then it would not clear the wall because it would hit it, or it would have hit the ground well before if the value was negative. Now, the second part of this is similar. It's just going to add an extra step in. So I'm going to leave everything that we have here from the first part. I'm just going to add in blue this change. So it said that assume there's a wind gust of 10 feet blowing in the face. So it's going to be minus 10, okay, because if it's blowing in your face, it's going to slow down the tennis ball. That's going to change this equation right here because we'll have a minus 10t. I would have to factor the t's out, and that would give me a, I will write it down here in the interest of making it a little bit cleaner. Got that cosine 18 minus 10 because we factored the t out and then divided the whole thing over. So when I type that in the calculator, I should get 2.63 seconds. Again, I will store it, and again, plug it into the y equation to see what I get. So I got approximately 13.9 feet. That is not bigger than the 20, so this will not clear the wall. And there you have it. That's the basics of projectile motion.